Hello, welcome to my channel. My name is Felipe, and today we are going to study the behavior of pure inductor in AC circuit. If you don't understand something about it, don't worry, try to watch another of my video. They are in Spanish, but anyway, I'm sure that you will understand them perfectly. Also, let's begin. First of all, try to imagine that you have an electrical conductor, cable for example, and there is a current flowing through it. In consequence, there is a magnetic field. Magnetic field in an area or surface becomes magnetic flux. Now, if you take the same electrical conductor and you start turning along the cylinder, you get an element called coil. The coil isn't an inductor, but if you are using a material with any electrical resistance, the coil becomes the pure inductor. The inductor has inductance. If you remember, the inductance opposes any change in current, and it is the physical property that links magnetic flux and current. We are studying in AC circuits. It means alternating current, so that we can use a sinusoidal function, for instance, so that our current now is A of t equal a peak in time sine of omega t. Now let's look at this equation again. L is our inductance, that is a constant, so that we can rewrite this as the magnetic flux is equal L, that's a constant, times current. But this equality is true if and only if the magnetic flux is a sinusoidal function too. That conclusion is important because it means there is a rate of change of magnetic flux in respect to time. And if you remember, Faraday's law says there is a back EMF that opposes any change in current because there is a rate of change of magnetic flux with respect to time. In other words, there is an induced voltage, self-induced voltage, that is equal the times derivative of magnetic flux. So we had to do this to apply this equation in our current, so that now our voltage is V of t equal omega times L times, if you take the derivative of sine, you get cosine of omega t. In order to compare the voltage with our current, we can rewrite this as omega times L times sine of omega t plus 19 degrees. That is because this is the phase shift between two functions. But we can this term is inductive reactance, and that represents the opposition of alternating current. And we were talking about that constant, but omega is equal to P times F. F is a frequency measured in hertz, and the value of that depends on country. Sometimes it's 50, sometimes it's 60. But for this lesson, the value of that it isn't important. The important is to understand the concept. Now let's look at these two graphs. I think this is the hardest part to understand because you have to use your imagination, because actually you cannot see the phasors. You can see this kind of waves using an oscilloscope, for example. Actually, you have to manipulate the components when you are using an oscilloscope with two channels in order to see both graphs in the same displays. But unfortunately, we cannot see this kind of phasor, this kind of mathematical tool. But to simplify our study, in this graph, we can see the voltage leads current by 19 degrees. In the same way, we can see the same in the time domain. When the voltage has the peak of value, our current is zero. Fortunately, nowadays, and for example, in my case, I like using Jupyter Notebook to make this kind of graph or calculating something. In addition to that, we can use AI to get the code. I have videos using both tools. I recommend you to watch. And for example, we can see the rotation of the phasors. But for today, I think the conclusion is the most important when we are studying pure inductor in AC circuits. That means the voltage leads current by 19 degrees. Well, if this video was useful for you, let me know in the comments. It will be helpful for me. Don't forget to subscribe, please, and like this video, and see you in the next one.